Next step is writing down an expression for that mysterious quantity J. So for J, we're going to use the electromagnetic energy. And since we're working with phasors, we're looking at the time averaged electromagnetic energy. So thanks to Mr. Pointing, we know that we can write this energy as an integral of the following quantity. So of the electric field, the conjugate of the displacement field, and then minus HB complex conjugate. And this thing we integrate out over our domain, which is in our case a 1D domain. Now we're going to make a simple simplification here. Namely, we're going to say that our epsilon and our mu, they're real valued. So there's no losses here. And this means that we can pry epsilon and mu outside of this complex conjugate, so that we can also write this in a much more simple way. By the way, I forgot a factor 1/2 here. So we can write this as epsilon times the magnitude of the electric field minus mu and then the magnitude of h squared dx. Okay. So this is the quantity that we need to calculate. But let's simplify this a little bit, because we have both the electric field and the magnetic field here. So what I suggest you do is pause the video and use Maxwell's equations to get rid of the electric field. And we're also going to say that we are going to look at the situation where the magnetic field H is Tm polarized. We're going to say that this is basically just a field which is only oriented along the z direction, with a scalar magnitude h, which basically is the psi in our problem formulation. So pause the video, get rid of E, make use of the fact that we're studying Tm polarization, and see if you can simplify that expression above. Let's see. So Maxwell tells us that the curl of the magnetic field in the frequency domain and in absence of sources is j omega epsilon E, right? So E is basically, unsurprisingly, 1 over j omega epsilon curl of H. And if we now look at the specific form of H, which you see up there, then we can easily calculate that curl. So remember, for the curl, we look at the following determinants, so unit vectors along the 3 directions. And then we have partial derivative with respect to x, y, and z. In our case, there's only a derivative with respect to x, so this becomes a normal derivative. Stuff only varies as a function of x, so that's nice and simple. And then in terms of components of H, we only have a component along Z. So it's a very simple determinant. The only thing that we have left here is then basically minus dH dx along the y direction. Okay? So now that we have this, we can simplify the expression for the electromagnetic energy. So the energy becomes 1/2. And then we have the integral, and then we have epsilon. And we now look at the magnitude squared of E. So that's the magnitude squared of this thing here. So for the denominator, we have omega squared epsilon squared. So remember again, epsilon is a real valued number. Okay. And then obviously we should not forget then the magnitude of the curl here. Then the minus sign drops. It's basically then the magnitude of the derivative of H with respect to x. Right. And then we have our minus mu, the magnitude of H squared. And then this whole thing is integrated out over x. Almost there. Let's remind ourselves of the fact that we're working in a situation for this simple demonstration here where epsilon is constant over the entire domain. So this means if we're looking for situations where the energy is minimized, then we can just as well multiply that energy with a constant. And in our case, that constant we're going to look at is 2 omega squared epsilon, so that we can simplify this a little bit and end up with an expression for J, which gets rid of this factor 2 here. And it also then gives us dh squared dx squared minus, and then we get omega squared epsilon mu, which we know is k squared, and then we have h squared dx. Okay. A final cosmetic operation is that also in case of lossless functions, you can actually prove that you can make a scalar multiple of h in such a way that we can replace the absolute values here. So for example, h squared, that we can just replace that with h squared, and the same for the derivative. We're not going to do that, but that's something that you can do in practice. That simplifies things even more. And if you then also remind yourself of the fact that h is basically the unknown quantity psi, to be consistent with the earlier notation, then you can say that the energy is the integral of the psi dx squared minus k squared psi squared, integrated out over dx. So this is the form of j that we're going to use, the quantity that we're going to minimize. Okay, so how are we going to minimize this? Remember from a previous step, we've introduced linear interpolation here, so we only have a small number of unknowns, 2 unknowns per node, 2 unknowns per element, basically. And psi, if you look back at the previous video, had an expression like x1 minus x divided by, x2 minus x1, and then the value at the left, and then we had something similar over here. So basically we had an expression for the field which involves these 2 unknowns, but then basically a linear interpolation between the 2 values at the edges of the element. So you can take psi, plug that into this equation. You can also calculate its derivative. It's going to be very complicated and cumbersome. We're not going to do that. Then you need to take the square of this entire mess and then integrate this. Very tricky to do. Well, not tricky, very straightforward algebra, but rather boring and easy to make mistakes. So let's not do that here, but let's rather focus on the general overall structure of the results that we're going to get. So the important part to realize is that, okay, psi depends linearly here on our unknowns. And if we square that over here, and even after integration out over x, we're going to end up with a bunch of terms involving, for example, psi1 squared. And we also have psi2 squared. And then we also have the mixed product psi1 and psi2. So it will be a very complicated expression involving terms like these, with some prefactors coming from what you get after integrating out this mess over x. Okay. So that's the general structure, and actually you can write that in a more matrix-oriented form. So if you say that we're going to restrict ourselves to the contribution of a single element L to J, which is basically what I've been doing here. This is just a single element. This was just element 1, but let's now generalize this to an element L. So this is actually going to give us a bilinear form, right? So if we have, for example, a column vector of our unknowns, and let's call these psi 2L minus 1 and psi 2L. Does this indeed correspond with, for example, psi1 and psi2 for the first element? Well, you see if you have L equal to 1, if you call the first element element 1, and indeed you get psi1 and psi2. So this is how we generalize this to any element. So we have then this column vector over here, but then we also transpose that to get this guy, psi2L. And in between we have a certain matrix A, B, C, D, with A, B, C, and D unknown coefficients. Well, they're not really unknown, but you can determine them by doing this nasty integration. But you can easily see that if you evaluate this, then you indeed get again a structure which involves the square and the mixed products of all of this, these quantities over here. So this is just a way of writing this expression here in a more matrix-friendly form. And matrices are very useful because that's the language we use when we implement this stuff on a computer. Okay. Now that was just for a single element. Obviously what we're interested in is the total energy of the system, so the energy that we get when we sum the contribution of all the different elements. And there's an exercise to show that this is basically giving rise to another bilinear form with a matrix which is a block diagonal matrix. So I'm not going to do that here. Refer to the video of the exercise. But the upshot is that you can basically write your total energy J again as some sort of bilinear form. So now not only of the 2 points involving a single element, but if we make a giant giant column vector collecting all of the different nodal values, so then perhaps we call this capital psi. We're working here still in the disconnected numbering scheme. So the first element gives you psi1 and psi2. Second element gives you psi3 and psi4. So as you see from these indices here, we collect all of these unknown psis into this column vector over here. Then over there we have then the the transpose of that, giving us this row vector here. And then we have a matrix in between, and you can show in the exercises, very simple, that this is basically a block diagonal matrix where each of the block elements consists of this little thing over here. But that's subject of this other exercise. You might remember from a previous step that what we really want to do is move from the disconnected numbering scheme to the connected numbering scheme. And the relation there is given by this connection matrix. So psi disconnected can be written as the connection matrix times psi in the connected numbering scheme. So finally, by doing that, you reduce the number of unknowns to only those in the connected numbering scheme. And then you get an expression that looks like this. Okay, again, we're only interested in the broad structure of this expression and not in the detailed values of this big matrix M here. But that's what you get basically when you try and calculate the total energy of the system, a bilinear expression like this.